I've done extensive work to look at the history of the Navier-Stokes equations, and it's kind of done in two parts for these videos, and maybe I'll add more later. One is a shorter overview and broad overview, and the second one is a deep dive, so expect a lot of content coming your way. So the first one we're going to look at is a broad overview of the development and history of the Navier-Stokes equations. So way back in 1738, the term hydrodynamics first appeared. And in my view, well, dynamics is the study of motion, and hydro refers to water. So the word hydrodynamica is written by Daniel Bernoulli of the Bernoulli brothers in his landmark publication. And in that publication, he sought to unify the fields of hydrostatics and hydraulics. Today, hydraulics, at least in America, might refer to something like a system of fluids to maybe move things, but more generally, it could just be the study of fluid motion, in particular liquid motion. Hydrostatics, as you know, is the study where there's forces and understanding the internal stress of the fluid, the pressure, without mean motion of the fluid. So when we teach students the subject of fluid dynamics for the first time, we actually start with hydrostatics and then move into hydraulics. But maybe this is just because of tradition, and I think it might be better to teach students the equations of motion first and make assumptions and reduce them. Hydraulics itself is an ancient science that goes way back to the ancient days of Sumeria and Egypt with irrigation, and I think that's mainly what motivated them in their work. Which brings us to irrigation. And it definitely dates back to Sumeria. Here I've noted the 6th millennium in Persia, but this is also in Egypt and all over the Middle East and the world. The Iranians developed so-called qanats, and I'm not sure about the pronunciation of that word, which spread throughout the known world, at least, not North America and South America. And they developed some basic mechanical machines which use hydraulic power in pumps, and these were developed by Hellenistic scientists in Greece and, of course, by Romans for aqueducts, and these still stand today in the test of time. More modern hydraulics were developed also in Italy in the 16th century and the 17th century in theoretical methods by Castelli and Fontana. Probably more last names that are Italian that I just am not doing you well of pronouncing. I'm sorry about that. Let's look a little bit more at the hydrostatic developments. It's definitely an ancient subject, like hydraulics and irrigation, and they really were driven perhaps by boats, but they wanted to understand buoyancy and why certain objects are propelled upward against gravity when submerged, and that was really explained and studied by Archimedes in the 3rd century. Pressure, or the internal stress of the fluid, was examined in the 17th century, much later, and it was an idea connected to a definition of fluid, where a fluid is a substance that continually deforms under a shear stress. Hydrostatics itself does not generally have a shearing stress. It does have a normal stress and this internal stress of the fluid, which is the pressure. So that would be like tau 1,1, tau 2,2, tau 3,3, and P. And we know that not only does this exist through the whole fluid, but it also exerts a force on the side of a vessel or something. We also notice that gravity causes the liquids to exert pressures on the containers, as well as anything else in the liquid. And this static pressure is really transmitted in all directions. And for some reason, it increases with depths. And this was really established by Pascal. But that was in liquids, like oceans and rivers. In the atmosphere, maybe that wasn't as intuitive. And Torricelli invented the barometer, and that gave us an idea of what atmospheric pressure would be in the gas which we live in, which is air in the atmosphere. So we could understand the changes as atmospheric pressure, which these measurements, of course, led to eventually a lot of interesting things in weather prediction. In the 17th century, Newton in 1678, of course, changed the field of mechanics. And in that time frame, he invented many things, including his own theory of aerodynamics, which we show in high-speed flow type classes does have an application. But, a fluid is not like a system of billiard balls that just imparts momentum and has separation. So that, analogy of Newtonian mechanics against a fluid just did not necessarily work very well. Aristotle had the idea that there might be a uniform velocity or proportionality that described motions, and it was definitely criticized by medieval authors, but I wouldn't be too concerned because, medieval authors criticized everything because of the dominance of religion in medieval Europe. But nonetheless, Aristotle showed and was picked up this concept. So it's sort of like this idea of momentum was really published by Huygens. It was not necessarily put forward by Newton. I mean, certainly there's lots of scientific communication happening in that period, and that's detailed in all kinds of interesting papers that you might find online if you go down the rabbit hole. Now, hydrostatic pressure was examined by Pascal in 1648, which came before Newton, so that force was known. And, of course, that resulted in additional work by Stevin in 1586. So this physics was really reshaped in the 1600s with the ideas and devices for measurement and extensions of mathematics. We'll stop here and read a quote by Galileo, and he wrote that philosophy is written in this grand book. I mean the universe, which stands continually open to our gaze. But cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand the single work of it. Without these, one is wandering around a dark labyrinth. And it's interesting, he has had many drawings of his ideas of turbulence and thoughts on turbulence in his notebooks, which have been scanned and many are published online. And he worked in this field in ideas of flight and aerodynamics. He's also had laid down an ideas of how to make flying craft by studying birds and fluid dynamics separately and combining them. He even incorporated the idea that one might need to lay down in a flight vehicle, much like the Wright brothers did and other earlier aviators. In the 17th century, there was a lot of mathematical advancements that were needed for fluid dynamics, including new ideas in algebra that allowed symbolic calculations, more so with variables. Descartes created algebraization of geometry, which is known for connecting these fields. And also important uses were Fermat's rule for maximum minima and Barrow's duality. And all these things really built up and led to the idea of the invention of calculus by Leibniz in Germany and Newton in parallel. We've mentioned Archimedes. He lived from 287 to 212 BC in Greek. This is an idealization of a painting by him. Obviously, he did many things and was one of the greatest mathematicians and impactful people of all time. And he proved many theories in geometry and everything, but in terms of fluids, he invented the screw pump, or came to being of it. And the Fields Medal, of course, contains his portrait. And there are some interesting quotes by him. Another name we just mentioned is, of course, Aristotle. Greek. There's no great genius without some touch of madness. Maybe there's some madness in creating a class on the Navier-Stokes equations, or Navier-Stokes equations, depending on where you're from. We've already mentioned Daniel Bernoulli in 1700 to 1782, Swiss. There's, I believe, an engraving of him on the right. Mathematician, physicist, and obviously he's probably the more prominent brother of the Bernoulli brothers, and foreshadowed a bit maybe his father and his brother. But Daniel Bernoulli has also made a lot of great contributions, his brother, especially fluid mechanic contributions, probability and statistics. And understanding probability and statistics is critical for understanding turbulence today. We've already mentioned his contribution to fluid mechanics. And many people in high school physics have probably heard of like the Bernoulli principle, which is the Bernoulli equation. Conservation of energy type equation can be derived from the Navier-Stokes equations and energy equation once you understand them. He definitely was a friend and wrote letters between himself and Leonard Euler. And he made this amazing publication called Hydrodynamics, which we talked about earlier, and the origin of that type word. And many people, I think this is like the foundation for the kinematic theory of gases. He also developed the Euler-Bernoulli beam equation, which some might solve if they're in engineering, numerically often. Johann Bernoulli, also an engraving on the right, 1667 to 1748. Compare the years, 1700, 1782, 1667 to 1748. And, of course, he's the Bernoulli family, and he worked on infinitesimal calculus. Interestingly, if you don't know the doctoral advisor of Leonard Euler, it was indeed Johann Bernoulli. And he was a bit of a jealous person in my reading and very competitive with his brother Jacob and son Daniel. Anyway, the father and son trio both published works on hydrodynamics, but Johann unfortunately had some errors in his and maybe also kind of misstated his work. And I don't really know the why that is, but maybe someone can write me and tell me, but I think it might have just been trying to get first to publication. Interesting, he also tutored L'Hopital in math, and we all learned that rule in Calculus 1, at least in the United States, and he did some publications on this. Let's go back to the pressure examinations of Pascal, who we already mentioned. And they tried to apply these types of rules to explain the new physics. The mathematicians were trying to explain physics. It wasn't so separate back then that there were this class of people called engineers who primarily work on fluid mechanics now. And the laws of statics were reduced to geometrical reason. According to Stevin in 1586, stated the hydrostatic paradox. So there's a lot of development in people. The hydrostatic paradox by Stevin in 1586 was a paradox. So the downward pressure of any given liquid is independent of the shape of the vessel and depends on its height and base. And then Pascal came along and he did a series of barrow experiments in 1646. Look at this date, 1586, and explained and observed through experiments by Pascal in 1646. Part of the reason why pressure bears the name of Pascal as the unit. What was the barrel experiment? Well, Pascal inserted a 10-meter long tube into a barrel, and the barrel already had water in it. And when the water was poured into like a vertical tube, there was observed an increase of pressure, which caused the barrel to burst, an exploding barrel. Anyway, you needed calculus to understand these laws of particular dynamics. But the barrel experiment corresponded well with the earlier observations of Stevens. Now, one of the first laws of fluid mechanics was actually proposed by Torricelli and a flux in 1644, which is about the same time as Pascal's barrel experiment. He wrote that the speed of a flux of a fluid through a sharp-edged hole at the bottom of a tank filled to depth h is the same as the speed that a body would require in falling freely from the same height. Let's think about that. The speed of the flux of a fluid through a sharp-edged hole at the bottom of a tank filled to depth h is the same as the speed that a body would require in falling free from the same height h. And think about how we can use our modern equations. And these types of lessons are not taught explicitly or from a historical perspective in like Fluids 1, which most people's first fluid dynamics class. And we develop these equations like from hydrostatics and simple one-dimensional equations. But the rules hold, and there's like an observation. Later on in 1675, Vergnon developed analytical dynamics by using Leibniz's calculus in the inertial mechanics of Newton's Principia, and proposed a derivation of Torricelli's law based on the momentum principles. The derivation was based on the hypothesis that the force causing the outflow was given by the weight of a column of water over an opening. And this was actually proven false. It was a very common mathematical derivation. Daniel Bernoulli, used in his Hydrodynamica, is a bit unique. It doesn't rely on the momentum principle, but it did use this new theory of calculus. The Leibniz theory was supported by Gravesande, who in 1722 made an experiment in which brass balls were dropped with varying height and measured the impact in the clay. Found that the penetration depth was proportional to the square of the speed of the impact. And of course, square of speed at impact of the brass ball is related to energy. And this is a very interesting basic relation. It reminds me very much of trying to find impact crater depth from, say, rocket exhaust on lunar landing on Mars and the Moon. Similar ideas. Jean-Roland d'Alembert wrote in 1757 on the publication of Hydrodynamica, and they were not friends, believe me. One can see through various memoirs that can be found in the volumes of the Sciences Academies in Paris, Berlin, and St. Petersburg, how the principle of conservation of living forces eases the solution of many problems in dynamics. We believe that there has been a time when one would have been most embarrassed to solve many of these problems without using this principle. Bernoulli was the first successful attempt of mathematical derivation, Torricelli's law. It contained other results in hydraulics, such as the prefiguration of Bernoulli's law that explains how pressure exerted by moving fluid is lesser than the pression of the fluid at rest. The pression. The Hydrodynamica was non-conventional and definitely caused a stir in many discussions. And these discussions amongst letters and conferences and correspondence is focused on what is the meaning of forces that put the bodies in the motion, and in this case focusing on the hydrodynamics. Isaac Newton and his followers had the view, or Isaac Newton's followers, that there's this variation of momentum, and this would give some sort of rule to acceleration. And that's definitely quoted in Isaac Newton's second law in his Principia. The change of motion is proportional to the motive force impressed, and it takes place along the right line in which that force is impressed. In Germany, Leibniz used the notion of vis visa and vis morta and expressed the laws of motion as a conversion of vis morta into vis visa. The Bernoullis published Hydraulica in 1742 now, with the aim of changing his son's result rather with the help of Newtonian mechanics rather than Leibnizian calculus. Bernoulli had to precisely describe the acceleration of the fluid, and he was thus led to describe the conventional part, and the acceleration and the internal pressure, the pressure that the moving parts of the fluid exerted on the other parts. Jean-Roland d'Alembert at the time had some observations, and these are converted from French into English. Why should we appeal to that principle used by everybody nowadays, that the accelerating or retarding force is proportional to the element of the velocity? a principle resting only on that vague and obscure axiom that the effect is proportional to the cause. He also wrote, the principle of equilibrium joined with the principles of the law of inertia and also of the composition of motions leads us to the solution of all problems where the motion of a body is considered. He then published The Trait to Fluids, where he applied his dynamical theory to the proof of the Bernoullis. In the works of the Bernoullis and D'Alembert, they considered the fluid to only have 1 degree of freedom, where it is decomposed into horizontal slices, and the velocity is uniform on each slice. This is sort of like a one-dimensional flow with variation of cross-sectional area. In 1747, he developed the concept of the velocity field, and that is actually the vector field. It's his invention, along with partial differential equations. And this velocity field of the field variables depends on the particular position. This is the origin of the velocity field for fluid dynamics done by D'Alembert. The partial differential equations, which he invented, he was the inventor of partial differential equations, were then turned into partial differential equations, a conversion. Anyway, today he's of course known as the pioneer of partial differential equation in mathematical physics. And he did this with his famous wave equation, which he wrote and provided the solution for, the one-dimensional D'Alembert solution of the 1D wave equation in 1749. So he was the first to use the partial differential equation in the context of mechanics, specifically for fluid mechanics in the wave equation, and the inventor of vector fields. In 1768, sometime later, he observed that his theory of invested incompressible fluids would lead to a paradox, and notice the assumption of incompressibility. It led to a paradox, which is the celebrated D'Alembert paradox, which is basically taught in every first-year aerodynamics class in the United States. For example, if you had an axisymmetric body with particular symmetry in the axial direction, and it's an inviscid incompressible fluid, and it's moving at constant velocity relative to the fluid, it would be shown that the drag force is, of course, 0. This is the paradox. And of course, it doesn't agree with experiments at all because there's always drag, but notice that there's these particular assumptions. So we knew that there was problems. He was not an idiot, and many people dismiss him today who don't know anything about the history, which is unfortunate. He wrote, thus, I do not see, I admit, how one can satisfactorily explain by theory the resistance of fluids. On the contrary, it seems to me that theory, developed in all possible rigor, gives, at least in several cases, a strictly vanishing resistance, a singular paradox, which I leave to future geometers to elucidate. And this is really his discussion on the paradox. But don't think that's his contribution, because he was the one who laid down in partial differential equations the idea of the fluid. And it wasn't incompressible, and it was picked up by Leonhard Euler later and corrected, which is why we now look at Euler. So Euler was very much aware of D'Alembert's contributions, and he used the idea from Isaac Newton of F equals ma, not in a vectorial form, force equals mass times acceleration. Maclaurin and Euler used Newton's second law in its full three-dimensional expression, and they applied Newton's second law to the mechanics of continua in 1750, just a few years later, 3 years later. And Leonhard Euler argued that no mechanical principles were particularly needed. Eulerian mechanics was a turning point in the development of the equations of motion. And Newtonian mechanics was definitely used originally as a kinematic theory for like particles, mass points, to be motivated of the motion of the planets. Particles, unlike Leibniz's work in Germany. And Euler extended this theory to the case of a continuous medium. In 1755, just 5 years later, he published this general movement of the fluid principles, where he applied his new theory and presented it. You can see scans of this document today on the internet. He was working on three-dimensional fluids that were compressible or incompressible, while generally the Bernoullis were working in lower dimensions and incompressible. But Bernoulli was definitely working in at least 2 dimensions and considered compressibility. Euler went on to describe the laws of fluid mechanics as applied to so-called fluid parcels. And that's why I often call these little boxes of fluids in 3 dimensions fluid parcels. We might call them little differential elements today. But they're just very, very, very small volumes that might be fictitiously isolated for analysis. And this is where the invention, of course, the Euler equations come in. He also created this idea of static pressure and internal pressure as the density of the force exerted on the parcel by the other parcels of the fluid. So Euler not only came up with the idea of these differential elements or fluid parcels, the Euler equations, which are incompressible, conservation, mass, and momentum, and he also came up with the idea of the internal or static pressure within the fluid, which are just 3 fundamental ideas that are so important to fluid mechanics. He further derived the Euler equation, and it can be written this way. So the left-hand side, of course, is the material derivative, working on density, plus rho times the divergence of the velocity field is 0. So this is the Eulerian conservation of mass equation. And he came up with a momentum equation, which is very much like the Navier-Stokes equations, but without a viscous term. You see there's a pressure gradient. So many people today say they solve with computational fluid dynamics to Euler equations, and they're really specifically talking about these equations: conservation of mass and conservation of momentum. Lagrange later discussed the importance of Euler's work, and here's a quote I pulled. Euler gave the first general formulas for the motion of fluids, based on the laws of their equilibrium, and presented with the simple and bright notation of partial differences. Partial differences. By this discovery, the entire mechanics of fluids was reduced to a single point of analysis. And if the equations which include it were integrable, one could determine the circumstances of motion and of action of a fluid moved by any forces. Unfortunately, the equations are so rebellious that up to the present time, only a few limited cases have been worked out. That means analytical solutions have been found. And so very early on, people like Lagrange were focusing on these equations and realizing that if you knew the initial condition and boundary condition, then at all later times, the future would be known. I think Simon Pierre Laplace would be very happy by this statement. Truesdell wrote, judged from a positive philosopher, Euler's hydrodynamic research are misconceived and unsuccessful. Their basic assumptions cannot be established experimentally, nor did Euler obtain them from numbers which can be read on a dial. Yes, after Euler's death, special solutions of equations have given us theories of the tides, the winds, the ship, and the airplane, and every year new practical as well as physical discoveries are found by their aid. Euler's success in the most difficult matter lay in his analysis of concepts. After years of trial, sometimes adopting some semi-empirical compromises with experimental data, Euler saw that experiments had to be set aside for a time. They considered phenomena too complicated for treatment then. Some remain not fully understood today. By creating a simple field model for fluids, defined by a set of partial differential equations, Euler opened us to new ranges of vision in physical science. It is the range we all work in today. It is this great insight, looking within the interior moving fluid, where neither eye nor experiment may reach. He called up the imagination, fancy, and invention, which Swift could neither in music nor in mathematics.